Hello student, today I am going to teach you about the Bellman-Ford algorithm. Bellman-Ford algorithm is very much similar to the Dijkstra algorithm. In Bellman-Ford algorithm, we also find out the single source shortest path, but in this approach there is a difference from the Dijkstra algorithm that in it we consider the negative edges also. It means in graph there could be the edges that will have negative weights. But important point before starting that how it is different from the normal Dijkstra algorithm. It is different from the Dijkstra algorithm that in Dijkstra algorithm negative weights are not allowed. But it is not so that we can design any graph with negative weight and we can solve it using the Bellman-Ford algorithm. Bellman-Ford algorithm has a limitation that it can handle negative edges, but it cannot handle the negative weight cycles. First of all, what is negative weight cycle that Bellman-Ford algorithm cannot handle? Negative weight cycle is the cycle situation. Suppose there are three nodes A, B, C, like this. There is a formation of edge here, and suppose we start and these weights are having the negative edges -3, -4 and 6. Suppose AB edge is having weight -3, BC edge is having weight 6 and CA edge is having weight -4. Suppose we start with a value 0 and we start performing relaxation over the vertices. Then 0 -3, B would reach at the value of -3. After that -3 plus 6, C would be relaxed at value 3. Now again, if we repeat this procedure, and if we repeat this procedure, what will happen? 3 minus 4 is equals to -1. Again, -1 minus 3 is equals to -4, right? And -4 plus 6, 2. Again in second iteration, 2 minus 4, -2, and -2 minus 3, -5, and -5 plus 6, 1, and this procedure will keep on going, and at no value the vertices will stabilize. So that is the problem with the negative weight cycle that occur in negative weight cycled graphs, that it cannot be solved using Bellman-Ford algorithm. So Bellman-Ford algorithm can handle the negative edges, but it cannot solve the negative weight cycle problem. So this is the introduction that the Bellman-Ford algorithm is able to handle negative weights, but it cannot handle the negative weight cycle. Now I am going to write the Bellman-Ford algorithm, and after that I shall take an example with help of which I shall explain you how does it work. Okay, so algorithm. Right. So here is the algorithm of the Bellman fold. Right. Now I am going to explain you. Now I'm going to explain you in Bellman fold algorithm. What we do, we consider that the source point, and the source point starts with a value 0. And the rest of the vertices in the graph initialize with a value infinity. The source value, that node we consider as the source, starts with a value 0, and the rest of the vertices starts with a value infinity. Initialize single source, we have started with a source. After that, for I is equals to 1 to Vg minus 1. Now for all the vertices except the source vertex, Vg minus 1 means all the vertices of the graph except the source vertex, we start a loop. And what we do in this loop, do for each edge uv for each edge uv belonging to eg, for every edge we relax UVW. So here what we do, for every vertex, for every vertex we relax all the edges with which it is associated, and relax what we do in this, for each edge UV belongings to EG, do if dV is greater than du plus W UV, means if the vertex can be decreased, vertex key value can be decreased with help of the edge, then that vertex is relaxed. Suppose if a edge is at value 5 and there is a vertex through which is connected to this vertex with the edge 3, and it is reducing its weight from 5 to 4, then in that condition we shall relax. But if it is increasing the value, then it is not relaxed, and this procedure is applied over every vertex of the graph. It means one by one, for each vertex we shall relax all the possible all the possibilities corresponding to different edges. So this is the simple algorithm. In simple word, we can start with a single source with vertex value initial value 0, and the rest of the vertex with value infinity, and in it we relax, and for each vertex we perform the operation of relaxation, in which corresponding to the every edge connected with that vertex we perform the procedure, relaxation. If it can be relaxed, it is relaxed, and we use negative edges also. And one point is important here. Suppose a vertex has been relaxed earlier, but through the upcoming vertex, if it can be relaxed further, then we relaxed it once again. Okay, so in this way, this is not greedy in terms. In this way, it is not greedy in terms, because it is using the every possibilities. It is not taking a decision, it is repeating a relaxation over a node after doing it once. So it is not greedy in nature. So this is the important point. Now I shall take an example, and with that example I shall explain you how does it work. Here I shall discuss you about the complexity also. Here what we are doing, we are considering the for I is equal to 1 to Vg minus 1. It means we are considering every vertex of the graph, and for every vertex, for each edge that's with which it is associated. It means for every vertex we are running this procedure for every edges. So it will take V into E step for every vertex, and for every it will take, for every vertex the number of associated edges it will run, so it will take mod of v into mod e number of computations. And here this loop, for every edge uv belongings to eg, this will run for e times. So definitely the complexity of this algorithm will depend upon the mod v into mod e is definitely greater than the mod e. So overall complexity is equals to, overall complexity would be equals to mod v into mod e in this case, right? O of mod v into mod e in this case, because this is the predominant terms and the complexity will depend upon this. Now I am going to take an example. I am going to draw a graph with help of which I shall explain you. Right. So here is a graph B A C uh, D D and E. Right. Right. Minus 1 4 3 1 2 5. Okay. This is minus 3. So yeah. So here is the graph. This graph is having 5 vertices, and there are 2 negative edges. From A to B, the weight is -1, and from E to D, the E to ED edge is having weight -3. So as I have told you that we will shall start with our source vertex. Suppose I have considered A as the source vertex. I have considered as a source. Then this will start with value 0, and rest of the node will be considered at the value of infinity. Okay. So I am drawing a corresponding diagram. So initially I initialize this diagram again. Here node A with value 0, and all the rest of the node will be at value infinity. The B infinity, infinity, infinity. Right. Now when I start from the this node, I am writing down the value 3 5 2 1 2 3 minus 1. Right. Now I shall have selected this node. So through this node there are 2 edges, and one is -4. So I shall draw a corresponding matrix with for it. Here the vertex are A, B, C, D and E. Now through the vertex A, the initial value is 0, and rest of the vertex start with value infinity. Right. Now from the node A, I can relax this node because 0 plus -1 is equals to -1, and this node definitely less than infinity. So this node can be relaxed to a value of -1. Right. This edge, and now 0 plus 4, 4. So this can also be relaxed because 4 is less than infinity. So here I have relaxed 2 edges. So 0, and this value has been updated by -1 because through node A and this node at value, this node was C at value 4, and rest of the node are not accessible through the node A, so they will remain at the value infinity. Right. Here I have used node A, and through the corresponding edges I have relaxed 2 nodes, and now this node has been utilized. Now after this I am considering that the node A has been used. Now I shall use the vertex B, and I shall check out that how many nodes can I relax through this. So through this node, now I am considering the node B because this node is at value smaller than the node C, the C node. Right. So I prefer this node. I shall choose this node. and through the B node there is an edge which can relax node C by value of minus 1 plus 3 2. So 2 is smaller than 4. Minus 1 plus 3 is equals to 2 and 2 is less than 4. So this will be relaxed. Minus, instead in place of 4, minus 1 plus 3 2. 0 minus 1. Now the next node D. This node is D. It is also accessible through the node B. So minus 1 plus 2. This would be at value 1. Minus 2 plus minus 1 plus 2. This will reach at the value of minus 1. 1 plus 1. So I shall relax this node by value 1. Okay. Now similarly this node is also accessible, that is node E, and minus 1 plus 2, minus 1 plus 2 plus 1. So this node will be relaxed to a value of 1. So now the graph will update like this: minus 0, minus 0, minus 1, 2, 1 and 1. So we have used this node also, and we have used this node also. Now we shall consider the node C also. So since this node, we shall use the node C also, but there is no outgoing edge through the node C. So this will not help in you any relaxation. So simply we shall get the same result for combination of A comma B comma C, 0 minus 1 2 1 1. None of the node could be relaxed by involving C into the procedure. So we shall opt for these two values, both are at value 1, but we shall consider the node. Suppose I consider the node D, then with help of D there are two outgoing edges, and now the value 1 minus 1 become 0, and 0 is greater than minus 1, so this edge is not relaxing anything. And this edge 1 plus 5 6, this node is already at the value of 2. So with help of node D we shall get the same result. CD 0 minus 1 2 1 and 1. Now the last node we are left with is the node E, and with the help of this node 1, there is a one outgoing edge which relaxes this node value 1 minus 3 is equal to minus 2, 1 minus 2. So this node will relax to a value of minus 2. Minus 2. So this will be relaxed to, so A, B, C, D, E. So 0, minus 1, the node that has been relaxed is D. So 2 and minus 2 and 1. But we shall check that whether this node is further updating any node or not. But minus 2 plus 1 minus 1, this node is already at that value. And minus 2 plus 5 is equals to 3. And this node is already at value of 2. So this node cannot be relaxed any further. So we shall relax this procedure, and these are the final values that these four. Yeah, I have not seen. So this node is at value 2, right? I have mistaken that I have not updated this node. I had not updated that node. So all these nodes are at their minimum value. The source node 0, the minimum distance that I have to travel to reach up to B is minus 1. Similarly to node C's distance is 2, and for node D is minus 1, minus 2, and for node E is equals to 1. So this is the basics about the Bellman-Ford algorithm. So it is very much similar to the Dijkstra algorithm. The only difference is that it uses it also used for the graph having negative weight, but cannot handle negative weight cycle. The complexity of it is mod V into mod E, O of mod V into mod E. So this is that's all about the Bellman-Ford routing algorithm. Thank you.